All right, cool. And how's my audio today? My audio is not bad. You missed it, Matt. We spent like 40 minutes of just them listening to garbled mess my headphones. So, all right.
Today with Crystal.
Crystal, good. Good. I felt I was adding that video just to kind of clear out parts of it, which is up now. But I was clearing out that parts and I was like, oh man, like I can't believe you guys listened for that long, which is like I don't know if I could handle that. It was really hard to hear my own voice. So,
Well, it kind of got worse gradually. Like
mhm,
almost didn't even really notice, like the
mhm.
frog in the slowly boiling pot or whatever, until everyone like
Totally.
couldn't understand what you were saying.
That's it. You guys were being trained for 30 minutes of like how to like understand my voice from that garbled mess. Um, yeah. Okay. So cool. We'll talk about today. So this is from yesterday's one was time series and trends. So we'll talk about more for the modeling, and then we won't talk about auto correlation really too much. But just kind of remind us a little bit of what happened last time. We talked about time series. We looked at basically how in a time series it's basically a data set where its main focus, its focus is about the time. That we don't talk about it being essentially like data points. We really think about it as like, oh, a period over time. And so we can actually start looking for patterns. We talked about what's stationary. So when we see a stationary time series, that's usually what we want. And I think we started talking about how we can, when it's not stationary, we have trends, whether I think there's, we talked about, let's see here if I, oops, assessing trends. Nope. Types of trends. There we are. So we have like, our linear trend where we have something going up or going down. That one's pretty straightforward. Talk about exponential trends, okay, where things basically ramp up and how exponential trends tend to look linear at first. And then over time, usually we'll get this exponential curve going upwards. Again, these are things that we don't want to do or we don't like to have. Okay, we want to do analysis on it. Then we have periodic trends and stuff like this, where this is much more similar to going up and down, like a fluctuation. I think I keep mentioning about the carbon dioxide level or temperature is one where it basically goes up and down. And then we talked about basically assessing them, rolling statistics, right? We talked about the Dickey-Fuller tests. Basically a statistical test for a statistical test to see if something is stationary, to see if the time series is stationary. Okay. And then we talked about removing trends. So we talked about log transformation. So doing a log transformation, basically to get rid of, to make it more in a linear fashion. So you can kind of, I mean, not linear, but stationary fashion, right? Also, you could use, I think, we talked about removing trends with log transformations, right? I'm not going crazy. Trying to remember now.
I don't remember
No,
either.
no, we didn't. Okay, so good. That's what we'll talk about today. So that's good. So I did want to show you guys, I'm trying to remember. We talked about types of trends. We talked about time series. This is what I'm looking for. Okay. I got myself all my wires crossed. So last time we talked about using a time series, we went through a bunch of like resampling and stuff like this, right? And then I did talk about visualizing time series. So I wanted to show you guys this real quick because I mentioned last time, let's go just run it all. I mentioned last time that like stock exchange data is not the best for some of this stuff that we were talking about visualizing. So I wanted to show you guys what that looked like. So one particular one was the heat maps. We talked about using a heat map to kind of find these patterns. So before we plotted out each in a subplot, and this time instead of using the New York Stock Exchange data, I'm actually using the temperature data. So this is basically for each of these years. I think it goes from 1980 to 1981 to 1990. And you can see like, we can kind of see this pattern. Oops. We can kind of see the pattern in here, but it's not super, at least for me, I can kind of see there's a dip, around this area for most of them, but it's not super obvious. And this is where a heat map is really useful. And you can see, when we do all the plots at once, which is good, you can see like we have all these plots, we can see, they generally have a dip right here. But you'll notice that we kind of lose a lot of information for any individual year. We can't really see any change and stuff like that. We can just see an overall mess of things, which is okay for some things, but you might want some individual, like say, hey, let's check out this particular year. you'd have to graph a whole thing out or do some kind of fancy, you know, animation or selection or whatever. It can be a little pain. So one thing we can do is a heat map, which I mentioned last time. And last time we couldn't see the pattern, but now you can see a pattern a lot better. So you can see for each year, for example, it's very hot right here, it gets colder here, and then hot right here. Or actually, I think it might be, no, that's right. You can see basically as 0 through 365, it goes from hot to cold, and you can see each individual year now a lot easier, but also we can see the overall pattern is that, oh, there definitely is a colder spot right here. So this is what I was talking about, where using a heat map can be really useful compared to trying to compare it with line plots and stuff. I thought that was a useful thing to kind of show you guys. One quick thing too, I noticed, I don't know, like the temperature, again, this is not my data, this is actually from the curriculum. I noticed that the temperature is colder in the middle of the year, which tends not to be true, at least for us in the Northern Hemisphere. So maybe this data is like from like Australia or shifted by 365, not quite sure. So yeah, wanted to show you guys that. Cool. Any questions on this? Since I kind of
this is much clearer than
yesterday.
It's also funny that it's a heat map for literal heat.
Yeah, I thought that was pretty fun too. It just know that you can use a heat map for anything. I was thinking like, is that a pun? I'm like, well, not really a pun, but yeah, heat map for heat. So cool. Wanted to show you guys that. So now we can talk about our time series trends. And did we talk about the types of trends? Stationary, linear, exponential, right? Okay, I wanted to make sure I got this right. I think we stopped about right here with removing trends. I think we started talking about, it's all coming back to me now. We talked about the Dickey-Fuller test, basically a statistical test for a time series. And then I think we stopped right before removing trends. I wanted to go over this. So for removing trends, basically, I kind of came through a few things. So, okay, is it stationary? It's like, well, it's not stationary. So what kind of trend is it? A linear trend, exponential trend, periodic trends. Those are the most common ones that we'll see. It just comes out in the mathematics in that way. And then we talked about assessing those trends, saying, okay, is it actually stationary? One we can do is rolling statistics, basically figuring out like, oh, you know, we can essentially move that window of like average, and we can move that along and kind of get a better picture of like what's going on. This helps remove a lot of any period, basically any going back and forth, it kind of smooths out that area. And Dickey-Fuller is more of a statistical test, and you can use stats models to do this. I believe, yeah, I have a little coding example here, but the curriculum goes through a little more detail on that. And I think there's a good, there's a good document source right here. So let me go ahead and run all this above to make sure we're all set. Okay, in case there was any dependencies that I needed. And we'll talk about removing trends. So once we find there's a trend, right, cool. It's like, we really usually want to get rid of a trend so it's easier for us to model, okay? You can kind of think it's like, what we're trying to do is trying to get rid of we're trying to look at like, get to the point where it's just noise, okay? If you see something that's going up and down, you're like, okay, cool, but I want to see, you know, how does it vary throughout time? Like, can I model off of that, okay? So we can try removing these trends. And again, the most common things that we'll try to remove are seasonality, basically where we have that period going up and down, like in our seasons of the year. And we'll also remove trends, like for example, if it's overall going upwards, okay? So our first line of defense is our log transformation. You'll notice that log is used a lot for a lot of these things because log just tends to, first of all, it tends to flatten things out. It basically purposely punishes higher values, which is usually what we really want to do. We want to bring that stuff down. Also, you'll see log, not necessarily for this thing, but I just want to say, like, you'll see log a lot of times when we want to convert something to multiplication into addition. Addition's a lot easier for us to deal with compared to multiplication. Of course, this is not related to this, but just saying this is why you see log a lot. So you want to panelize higher values, log transformations. Notice that we can also do square roots and cube roots, you know, higher roots. Usually past a cube root, at that point, you're kind of like messing with data too hard. Usually square or cube root. Usually square root's more common. I mean, I guess I've seen some cube roots, but usually it's not. After basically the kind of rules like, well, if you're getting too high of a power, it's kind of like, well, maybe we need to try something else, okay? But just know that these are some alternatives too. And so, sorry, I lost train of thought, but this is really useful when there's a clear and positive trend, but it's not linear. So like clearly like it's going up, but it's not going in a linear fashion. For example, an exponential trend, which you guys probably know, oh, exponential, usually you think of, you know, Euler's number E, right? E to some power. That's usually what an exponential looks like. So if we do a log, we can get rid of the exponential. So at least then we can make it more linear. Also, when it's like there's certain we're for sure that it's heteroscedastic. So again, heteroscedastic, which I looked it up afterwards. I guess you can spell it with a K, which is weird. I didn't know there was 2 ways of spelling it. But I remember this one's probably the one that's I think messes up a lot of people. But if you remember back from like when we were talking about residuals, the residuals change over time. So for example, if we have a plot of all the residuals, we have very low values, and then over as we increase our X value, we get higher and higher residuals. Basically, it's saying that that variance is changing over time, right? That's what really this is trying to say. It's like, hey, we're having a larger change over time, which means there's some time dependence, and we kind of don't want that. We want it to be stationary. So let's clear this. So we can, oops, I have to actually run it now. There we go. So let's go ahead and run this. So what I did here is just basically doing a plot, our time series, which I defined up there. And I think I have, okay, I have no transformation. So I think if I remember this right, it will be, well, we'll see what it looks like. But it's something we had for, oh, monthly sales. So, okay. It's from data that we already looked at before. So basically the very first one I have is basically no transformation. So you can see basically kind of going up and eventually kind of goes more of an exponential. Like it almost looks linear, but if you look at it closely, like it goes linear and then kind of ramps up. So we have a slight exponential curve here. It's kind of hard to tell, at least when I view this, is that you can kind of see it going, I'm sorry, for the log transformation, you can see now it's still going up, but we're still getting that linear fashion right here. So it looks like, okay, good, we're moving it to a little slightly better thing. One problem though you can notice is that if you look at the log transformation here, is that the variation right here, you notice the variation is pretty good right here all the way through. But here you can see that the variation gets smaller and smaller. So basically we have a heteroscedastic here. So like, we don't want this. So one thing I tried is like, okay, let me try to do a square root. And the square root might do a little bit better job. It's arguable. Of course, you would do more firm testing with saying, you know, stationary, but you can kind of visually see, it's like, hey, like it's looking linear. It's not perfectly linear, but it's pretty close. And it looks like we removed some of that heteroscedasticity. I can never say that word, but you can see that we got rid of quite a bit of that. It's still kind of there, but it's getting in that right point. And our goal really was to make it stationary. So there's a few things we can do next, okay? So log transformations or some kind of transformation usually is kind of a good go-to because it's easy. Like you can see all I did here is an np.log, okay, of the time series. So it's like really easy. I didn't have to do anything, but of course it didn't fix our full problem. So our next step, which is really common, is basically subtracting the rolling mean. So we talked about the rolling mean with how that works. And so we can actually take the rolling mean and basically take out that part. And what the idea here is we're removing some of that, seasonality to it. So we can kind of see right here, I just have, first I do a transformation of the square root. Since it did a pretty good job, we'll keep that transformation in there, and then we'll try doing the rolling mean here. And so just know that we're just plotting it out. This is just all the plot, right? But you can see I have a rolling mean of about a window of 4. So it's going to take the last 4 points, and it's going to average those together and put it together. And then you can see I have my rolling mean, my data transformation. So we can hopefully see this a little bit better. So you can see here, here's my rolling mean in red, and here in the blue is my actual transformation, the square root transformation. So you can see like, okay, we smooth this out. So now we're actually gonna try to subtract this out. So I'll go ahead and run this part, and then we'll go ahead and drop NA. So the reason why I do a drop NA, just to make this a little clear, is that when I do, I'm not gonna do that again. No, I can do that. Data minus, so I'll just kind of show you, is that the first few elements, since I took out the first 4, you'll notice that the rolling mean isn't defined for the first 4. So that's because there were no previous 4. So there's a few ways you can handle this. One way is you can try to basically just make this last point exactly the same, so just be a straight line here. You could also, like what we do in this case, we're just gonna drop them. And people say like, whoa, aren't you dropping data? It's like, yeah, well, kind of. But in the end, we're also encoding some of that information with this rolling mean, and it's only 4 points compared to usually many, many points. So it's like dropping 4, that's probably fine, okay? And so you'll see here, NA, basically the first few points are not defined since we didn't have points defined for those points, or values defined for those points from the rolling mean. So I'm going to replace those things, and now you can see, I'll just get rid of this so I can show you. You can see now I have no NA, but we lost some of that information before. Okay, I'll keep it there. And then I'll go ahead and plot this out. So now we'll actually see the plot of this data minus rolling mean. And you can see here, we actually get something that's no longer that linear fashion. And the reason why is basically we're trying to get rid of this linear part, basically it's increasing. And the rolling mean isn't getting rid of this extra noise. It's mostly just getting the ideas like, well, if the first 4 points are pointing in the direction of going upwards, we're going to get rid of that upward trend. And so that's why we end up getting something that looks much more stationary. You can tell right here. Cool. Any questions you guys have?
What is your, so I see you made it stationary, but what does this reveal to you now about the sales that you couldn't see before?
Good, yeah. So going like from the very beginning, like from the very first part, we can see, oh, sales over time went upwards, which is good. It's like, oh, that kind of makes sense. Like maybe talk to the business, for example, say, oh, we've been expanding for the past few months, you know, or for the past few years. And so it's like, yeah, because you're expanding, it makes sense that you're increasing upwards. So we're like, okay, cool. That can be explained with what we have. But like they might say, well, we don't understand what our fluctuations are, or like maybe there's other associated data with, you know, why we go up certain months and down certain months. So for example, is that we want to see like, we essentially want to find the noise, because the noise in a lot of ways could mean something if we have extra data. So you can kind of think of like the stock market is that you might see general trends. Like for example, the stock market overall tends to go upwards just because of basic economic growth. But it's like, well, that's not really important. We want to, like, if you want to actually predict stock prices, you want to see what's the little fluctuations, like, you know, even from like month to month, like what causes those things. And those things can be like, in that case, a huge number of factors. It could be about the news. It could be about, you know, commodities trading. It could talk about other stocks trading at different values, you know, things along these lines. And so basically what it comes down to is that we're trying to remove things that, you know, are essentially pretty easily discernible. So again, we can easily see this is going upwards. If there's a periodic kind of part, maybe like, for example, for sales in this case, maybe certain sales are, you know, like there's more sales in like December than there are like in February. Like maybe there's some kind of pattern that's every year is like that. We want to remove that seasonality because we can predict those parts. And at the end of the day, we get something that has basically, essentially, in a lot of ways, all we have left is the noise. We want the noise because we're hoping that maybe with other information, in this case, we didn't really look at that, but there could be other information that explains why these things go up and down. For example, maybe this downward turn, everyone took vacation. And like, that's something that we could look at from data that we have.
So it's like you're removing everything that makes sense until all that's left is the part that doesn't make sense. So
that's right.
I see. That's interesting because in the other ways that we've learned about cleaning data, you're taking away the things that don't make sense.
Yeah, it's kind of, it's an interesting one to like phrase this. I think in my view, like data science, what you're trying to do is, okay, so like for physics, like I'll go back to my physics side, is that when you're doing a physics experiment, you have a theory. You have basically an equation that is like, you know, a beautiful equation that will make these nice, beautiful like sine waves. But the problem is that you don't have beautiful sine waves. You have little noise and stuff like that. If you ever use an oscilloscope, for example, to basically look at these kind of wave patterns, there's a lot of noise and little extra stuff. And so in physics, in a lot of ways, you say, well, we want to see, does the data match our theory? But in data science, you're kind of doing the opposite. What you're doing, you're starting off with the data and you're saying, can I create a theory? Basically, can I create an explanation of this data? So in physics, a lot of times, like, well, we know what the theory is. It's like, well, why is it all this fuzzy? It's like, well, it's probably electrical interference. It's probably because of this thing. You know, you can say like all these factors that add up to like why you have this little bit of fuzziness, why this randomness, and you're okay with that because your theory is overall put together. But the opposite is true for data science. We're like, well, we want to explain all of these parts the best we can. And maybe some of it's just random noise that in random noise, I mean, this is where it kind of like, this is where it's kind of, it feels very metaphysical sometimes, but like we like to say like, you know, the world is deterministic in some form or fashion. If this happens, something else will happen. It just turns out, you know, like, well, what level can you get to that? And that's what data science is trying to solve. It's like, well, what extra amount of information can we do to explain that, you know, quote unquote, random noise, but that random noise is actually something you can explain. So that's kind of like what's going on with time series. So when we're doing like that cleaning data stuff, ironically, like when you clean data, you're actually losing information, right? But a lot of times you're like, well, is that random noise that we can't explain? Like they won't be able to because the data's unclean. But in the end, basically, we're trying to separate, say like, okay, this factor is affecting this way, this factor is affecting this way. So yeah, it's good observation. But cool. Any other questions? I think Matt, you might have something.
Yeah, I think I could work out how the statistics of like a hypothesis test on a log transformed thing would change, but it's not so simple for a rolling mean thing. And also, doesn't the width of the window of the rolling mean affect that data quite a lot?
Oh yeah, definitely. So going back to your second question or second observation, let's say if I put something like, let's say 20, okay? So we'll reload the information, we're transforming it. So this should have, you see, this is our general guy right here, and we'll remove the head once we subtract it. So remove those NaN values, right? And we can now see if I run here, you can see we have more of an upward trend here. And that's because we averaged over too long a period. The real reason why we're trying to do the rolling mean is we're trying to get rid of that extra trend word, like that trend. But if basically, like, especially for an exponential graph, if we go further and further out, it's gonna lag behind that exponential, because the exponential is gonna go higher and higher and higher. So you can actually see, like right here, it's like does a pretty good job like writing in about the middle, like right here. But then as we increase further, you can see it continuously is underperforming, right? It's not finding that part, and that's why we end up seeing this more positive. Now, if we of course put a smaller one, like I'll go back to like 5. Okay, you can see now it's pretty good at matching about what the average is between these two parts. It doesn't do the best right here, but in general right here, it seems to do a pretty good job trying to figure it out. There's still a little bit upwards right here, probably because there's some huge jumps. You can see there's quite a few big jumps right here. But in general, it's doing a pretty good job matching it up. And of course, if we go into smaller, right, we do a window of 2, now it's matching really well. But then at that point, you're just averaging over 2 of them. So you're kind of not going to get any information. So you can see if I do a window of 2, and I plot this out now, I get a lot more noise. But in this case, I might not actually want this, just because it's matching too well to the data. So like obviously if I have a window of 1, right? Oh, it matches perfectly. Well, duh, because it's just the same point, right? So it doesn't do anything here. And if I, of course, there's nothing to drop. You can see it's like, oh, I have this general upward trend. It's like, well, that's not really useful in this way. So in a lot of ways, this window, it's kind of subtle exactly like what is the best window to use. And a lot of times it's with context. It's like, for example, if you have a trend that is yearly, you might want to have a rolling mean of like 6 months or 12 months, basically trying to get rid of that extra period in that extra part. And so you can try to level it out a little bit. Okay. So that was your second question. Well, I'm trying to remember what your first one that you had brought up.
I mean, if you presented, say that the noise thing, yeah, that image below there, if you were presenting that to your manager or something, and they asked, how sure are you about this data? How would you describe the statistics behind that?
Yeah, so at this point, there's a couple of things, right? One is I would explain like what I'm doing. I'm trying to get rid of these trends, so I can look at basically like what's this extra little noise that's going on. So that would be explain what I explained first. And then the second part would be like, okay, now that I have this noise, let's use the data that we know from like these dates to see if we can correlate some of those parts and predict those things. So at this point, this shouldn't look like any pattern. This shouldn't have any real periodicity, basically it should be stationary, right? And so if it's stationary, it means, okay, like you can imagine like now that it's stationary, it's standing still, it's not doing any period, it's not going up in a trend, I can go ahead and isolate and start seeing if other parts are correlated, other features are correlated with this, data. Does that make sense? Cool. So it's more like, I could do like, for example, a stationary test, like the Dickey-Fuller test, to see if like, oh, is it actually stationary? But for the most part, I can kind of look this very quickly. It's like, oh, this is probably stationary. I can do a little confirmation to say, hey, is it stationary now? And then once we have it stationary, then we can start doing using some of our other tools that we can do with time series. Okay, cool.
Okay, cool, thanks.
No problem. Yeah. Again, like it's kind of like, I think you're kind of at that right point where it's like, wait, we made it stationary, so like, why? Like, and basically it's come down, it's like, we're trying to, we're getting to the stationary point so we can actually do something with it. If it's doing those trends, it's a little harder to deal with because now we have to remodel those trends in the same way. Okay. So, and then one last thing, just to kind of add in here, the curriculum did mention a weighted rolling average or rolling mean. So this is also, let's see here, I think it's built into Pandas, exponentially weighted moving average. So, or weighted mean. Basically, it's the same idea with the rolling mean where we have a window, but you might, for example, have a decay factor where older values are punished more. So right here, we just did an average when we did our rolling mean. When we do our average right here, we're treating every point in the past for, the past 4 points exactly equal. But let's say it's like, well, we want, the past to not have as much effect for the average. We could do something like an exponential decay where we say, okay, well, the ones further in the past shouldn't matter as much compared to the ones that were like just yesterday. So it's kind of like the idea is like, the weather 10 days ago doesn't matter as much compared to the weather just yesterday. Of course, 10 days ago will still give you a pretty good idea. Like if you're in the middle of January, it'll be a lot colder if you're in the middle of June. So obviously 10 days will help, but it won't help as much compared to the weather just the day before. Okay, so that's where the exponential, or sorry, weighted rolling that mean is. So just kind of know that that's options there. And there's good documentation there. And I think the curriculum doesn't talk too much about it, but just know that that is something you can do. All right. So this leads us to, again, removing our third method for removing our seasonality and trends is differencing. And this is probably the most common one that basically we do. And it uses the idea of lagging. So we actually kind of started getting into this point. Like you notice we transformed into square root. We also did a rolling mean. And essentially we're taking off, we're taking off some of that information from the previous parts when we're doing that rolling mean. So lagging is kind of like the same exact, well, not the same exact thing, but that same concept. We're taking previous values and subtracting that off from our current values. And we plot the difference between those points. So it's kind of easy to just kind of show you guys. So basically here, I'll have our difference. So our data diff is basically taking this TS, our time series .df, and this periods. And this periods right here basically is telling us, what's it called? Like how frequently we should subtract this part off. Again, there's more documentation of like exactly what we're talking about here, but just know that this period's right here saying like, okay, we're trying to get rid of saying how often does this period happen? So we're subtracting off this part, and we can see just off the bat, just by doing this one thing, we can actually get a pretty good, like looks pretty stationary in this case. And we can do a test, to double check. And basically it's just lagging off the extra points. So I think I have another example with temperature over decade. So let's see if this is the one I'm thinking of. Yes, okay. So you can see this is temperature over decade, and you can see every year, what you would expect with temperature, more or less goes into a pattern, cold in the winter, hot in the summer, and so on, at least for the Northern Hemisphere, okay? So going over and over, right? And so you can kind of see like, well, there's definitely a periodicity in here, I would like to get rid of it. So I can actually do our data.diff, and because the period, in this case, is 365 days, basically, it should repeat itself about every 365 days, okay? This is all context, okay? I can actually remove it, and you can see there's still like, some noise, but it's relatively stationary. Like there isn't like any clear pattern that's, being regulated. It seems relatively noisy, okay? Which is what we want, which ironically is like, we want noise so we can actually do something with it compared to this period right here, which we can explain pretty quickly, okay? So again, this is probably the most common way is doing differencing. It's basically taking the previous points and subtracting off. It's kind of like moving that rolling mean window, okay? Well, any questions on why or how I should use this?
So if your data were already stationary and you tried to difference it, it would just look flat. There wouldn't be any differences, right?
Yeah, let's try it, okay? So let's do a data.diff. Okay, I'm just repeat it, right? So since we already made it relatively stationary, we'll do the .diff on top of that again. And yeah, nothing really. You could try doing it again. It's basically, it will more like remove parts that are like being repeated over and over again. You can see even after doing that difference 1, 2, 3, 4 times, it's still not that much more stationary. Again, there's more details in the actual documentation of exactly what's going on here. But something to play around with. That's an interesting point. One thing you might notice too with .diff, I did this periods. If I do like a lower than it should be, you'll still get that periodic function in there, but it won't be as clear. And you can see that it's a lot harder for us to see what's going on here. So this period is really important to understand, like, what is the context, like what is that period that we're going over and over again. The default is just 1, which like if I do just like 1 here, which is just the default, you can see it just doesn't, it helps, but it's not really giving extra context. And that's why we do 365 here. Is it's basically of the context of saying, well, we know it's repeating every year and getting rid of that period, that seasonality to it. Okay, so cool. All right, yeah, so okay, that was differencing. So our last part here before I move on to, actually, this is much more on sections 25 right now, but I think it's important stuff since we're going to use time series quite a bit. Our time series decomposition. So this is when we can transform a series into multiple series, which I think is one of the coolest things you can do. Basically, it's kind of separating out, like, see what's the seasonality, see what the trend is, and then we also have the noise. So that's usually what the 3 parts that we'll care about. And you can call it noise, randomness, irregularity, the remainder, residuals. You can think of like whatever like is not explained by the trend and not explained by the seasonality, is that's what's left over. So it's kind of cool is that we can do this. Now, one thing to note is when you do this, you need to identify if the model is additive or multiplicative. I can never say this word either. Too many consonants. But basically the idea here is that, is it being added up over time or is it being multiplied each time, like basically scaling up? So this tends to be sorry, I'm trying to read my own stuff. Usually when the distribution magnitude of fluctuations change. Yeah, so what you see is that over time, like for example, additive is like when the whole thing is moving up, but each fluctuation is about the same length. So maybe I should draw this out. This will probably be a little easier to see. So like additive tends to look like where we have like, you know, like if this is like, this is not multiplicative or additive, okay, you have something like that, just a, kind of a period, but you'll have something that's kind of like this for additive. So it's like about the same, like that same fluctuation each time, but multiplicative, when we have that part, we have more like something's like, and you can see it's like, oh, that part is getting larger over time or smaller in some cases, if it's a smaller than 1 kind of deal. But the idea here is that we have, basically it's being multiplied each time, which means there's bigger changes each time compared to just the whole thing being added up and moving up forward. Okay, so show you guys an example now. So we'll have the passengers as a new CSV, so we haven't seen this data yet. So this is basically, I believe it's from the curriculum, but basically the idea is the number of passengers, and I think the idea is that they've been expanding, I want to say it's for a plane, but basically like they've been expanding their business, so they have more and more passengers kind of deal. And you can see here, it's going up and down, up and down, up and down. And you can see like over time, we still have this fluctuation. Maybe, for example, more people travel during certain months than other months. And you can see it's up and down trajectory, but it's overall going in this positive trend. So what we can see here, and what did I plot out? Why did I plot out 2 of them? Oh, I did the log plot. So you can see here, if I do the log plot, I can get rid of that heteroscedasticity, right? It's no longer heteroscedastic. You can see, like, for example, it was kind of doing a bigger variance, and you see, oh, it's nice and even. So in this case, like, oh, we probably don't have to worry too much about it basically expanding outward. But you can see there's still a positive trend, and it's linear. Okay. So now what we can do the seasonal decompose, which is great for stats models. And note that most people don't know about stats models. It's not super common. So the stuff we talk about in the curriculum where stats models is pretty useful. You won't see too many people online using it too much, which means that the thing is like there's a lot of functions that are not built into Pandas, into Python, into a lot of even scikit-learn and stuff like that, that stats models has already put together. So just know that super useful package. So now we're going to decompose that log of the time series. And I'll have the trend, I'll have the seasonal, and I'll have the residual. Okay. And then I can actually plot each part out, and we can see each plot now. So now we have the original with log transformation. We can see this is the general trend, which we can kind of see that's our part right here. We can see the seasonality, so we can kind of see where that's repeated over and over again. And then all that's left is our residuals, our noise. And so it's a pretty useful thing that we can very quickly look at, basically decompose these parts of of the test. And what's nice, like now we can say, okay, we got the trend, we got the seasonality, and we have this noise, and then it comes down to say, hey, like, is it stationary? And the noise is the stuff that we want to like play around with now. So can we explain more of it from something else? Because there's no longer a period. And we can, again, check with it with a Dickey folder test. It's probably a pretty useful one just to check if it's actually stationary versus than just looking at it and saying, yeah, looks stationary. You know, it gives you a dry idea, but of course it's nice to say, how certain are we? Okay, so cool. Any questions on this stuff I went over for decomposition or any other parts that we went in for sections 25?
Yeah, I have a question. So does the stats models just apply the techniques that you showed us earlier in order to decompose it in these ways?
Yeah, there's some a little more advanced stuff going on here. So I'd say if you're really curious, definitely look at the documentation for the seasonal decompose. They do a few extra things that we were talking about, but essentially, yes, it's doing essentially the similar things that we were looking at and stuff like that one by one, but just more more automated and more mathematically like rigorous, if that makes sense. So what's nice is that you don't have to keep doing this yourself, kind of deal. Okay.
Does seasonal decompose work for multiplicative and additive noise?
Yes, so I believe there's an option model. So yeah, so by default it's additive, which makes sense for this one, right? Because in this case it is additive after we log transformation. Multiplicative, you know, if you had something where even after you transform it, you can see that there's definitely a change in that variation. So just know that and there's a bunch of other things that we didn't talk about, you know, these other parts. And this is where I'm saying there's a whole lot more to this specific function that could be useful to look at. Okay. Cool. Any other questions, guys? Okay, cool. So I'll stop this part and we'll talk about section 26.